Welcome to today's paper reading. Today's paper is titled, Training LLMs over Neurally Compressed Text. This paper, published on the AR14 preprint, explores the training of large language models over highly compressed text by Brian Lester and colleagues from Google DeepMind and Anthropic. In this paper, the authors explore the concept of training large language models, LLMs, using highly compressed text. Standard subword tokenizers offer limited compression, whereas neural text compressors can achieve significantly higher rates. Training LLMs directly on neurally compressed text would offer advantages in training and serving efficiency, as well as facilitate the handling of long text spans. The primary challenge is that strong compression often results in opaque outputs that are not conducive to learning. Specifically, text compressed via arithmetic coding is found to be difficult for LLMs to learn from. To address this, the authors propose a novel compression technique called equal info windows, which segments text into blocks that compress to the same bit length. This method demonstrates effective learning over neurally compressed text, showing improvements with scale and outperforming byte-level baselines in perplexity and inference speed benchmarks. Although the method yields worse perplexity than subword tokenizers for models with the same parameter count, it benefits from shorter sequence lengths, which require fewer autoregressive generation steps and reduce latency. The paper also provides an extensive analysis of the properties contributing to learnability and offers suggestions for further improving the performance of high-compression tokenizers. The current training of large language models, LLMs, primarily involves subword tokens generated by tokenizers like BP or Unigram, achieving around 4 times compression over natural language text. These tokenizers obscure the character-level details of tokens, which is generally accepted due to the benefits of compression. However, this raises questions about whether further compression could yield even greater advantages. Autoregressive language models can act as lossless text compressors, and recent work shows LLMs can achieve 12 times compression. This leads to the question of whether an LLM could be trained directly on this neurally compressed text. In this paper, the authors explore using arithmetic coding, AC, to compress text, training a model M2 over this compressed text. They introduced the concept of equal info windows to aid in the learnability of AC compressed text, showing that this approach can make learning over neurally compressed text possible. Figure 1 illustrates the process of training a large language model, M2, over neurally compressed text. Initially, a smaller language model, M1, is trained to predict the next byte in a sequence based on the preceding context. This model is then utilized to compress a corpus of text into a bit stream by feeding its predicted probabilities into a compression algorithm such as arithmetic coding. The resulting bit stream is subsequently divided into tokens, typically 8-bit chunks, which serve as the input for training the larger language model, M2. This approach aims to leverage the efficiency of neural compression while maintaining the ability to model complex language patterns. Training large language models, LLMs, over compressed text offers several advantages. Firstly, it enhances efficiency by allowing the model to process more text for the same computational cost. This means that a model trained over C times compressed text will see C times more text during training compared to a model trained over raw text, given an equal compute budget. This increase in data often leads to improved performance. Additionally, processing text more efficiently reduces the serving cost for handling a request of a given prompt and continuation length, both during training and inference. Secondly, working with compressed text allows the model to handle longer contextual dependencies. This is particularly beneficial for applications that require retrieving content from a document or answering coding questions provided with documentation. Lastly, training over compressed text ensures that information is spread more uniformly across the sequence, allocating more compute to harder text spans, similar to adaptive computation time but with dense computation. The training data consists of English web text from the C4 dataset, where 128 documents are concatenated to form long sequences with an average length of 277,760 bytes. For compression, several methods are employed, including arithmetic coding using M1, static logits arithmetic coding, and equal information windows. These techniques aim to compress the data effectively for training the M2 model. The M2 model is trained for 200,000 steps with a batch size of 256 and a sequence length of 512 tokens, resulting in the training of 26.2 billion tokens. This setup ensures that the model is exposed to a diverse and extensive range of data, enhancing its learning capabilities. Figure 2 illustrates the process of encoding text under the equal-info windows method into a series of n-bit windows. Each window is determined by encoding the remaining text byte by byte using arithmetic coding until adding more bytes would exceed the target bit threshold, which is 16 bits in this case. Importantly, both the M1 model and the arithmetic coding algorithm are reset at each step, ensuring that no information carries over between windows. Table 1 illustrates the differences in compression ratios between token and bit levels. It shows that while larger vocabularies require more bits to store each token, which impacts absolute compression, the token sequence length is crucial for minimizing the compute used by an LLM. The table provides specific compression ratios for sentence piece and arithmetic coding, AC, with different vocabulary sizes, highlighting the trade-offs between token and bit compression. Table 2 illustrates how different approaches to weakening the model or coding components of arithmetic coding affect the compression ratio. The static unigram distribution in static AC, V equals 256, results in the lowest compression ratio. Conversely, equal info AC, B equals 16, V equals 256, shows an improvement in compression ratio as the window size increases. The standard arithmetic coding with a vocabulary size of 256 AC, V equals 256, maintains the highest compression ratio among the methods tested. Table 3 illustrates the performance of two trivial models in terms of bits per byte across various tokenizers. The uniform model assigns equal probability to each token, regardless of context. In contrast, the unigram model assigns probabilities based on the global token frequencies observed in the training data. The table highlights that compression-based tokenizers, such as AC and gzip, output a near-uniform distribution of tokens across their vocabulary. This uniformity is reflected in the minimal gain over the uniform model when unigram statistics are modeled. Consequently, learning over this data necessitates the modeling of longer contexts to capture meaningful patterns. Table 4 presents the model sizes and corresponding hyperparameter settings used in the experiments. The table lists the parameter counts for models ranging from 3 million to 2 billion parameters, excluding embedding table parameters. It also details the embedding dimensions, number of heads, number of layers, head dimensions, and MLP dimensions for each model size. This information is crucial for understanding the configuration of the models used in the study. The results indicate that simple methods of training over neurally compressed text, such as arithmetic coding with M1 assigning next token probabilities, fail to learn effectively. The model outputs a uniform distribution over tokens, which is denoted by the dashed line in Figure 3. This failure is not due to M2's inability to model M1, but rather the complexity of the arithmetic coding process itself. On the other hand, sentence piece emerges as a strong baseline, outperforming all other methods across various model sizes. This contradicts recent findings where byte-level models outperformed subword models at larger scales, primarily due to the metrics prioritized in each study. Additionally, equal info AC demonstrates significant performance gains, particularly at larger model sizes. This method not only achieves better bit/byte performance but also uses fewer flops/byte for a given model size, attributed to shorter sequence lengths. Figure 3 compares models trained over compressed text against baseline models in terms of bits/byte and inference flops/bytes. The arithmetic coding and static AC settings are essentially unlearnable, with models failing to outperform naive baselines that assign equal probability to all tokens. Equal info AC and gzip outperform naive baselines and show improvement with scale. Equal info AC is the strongest of the compression-based methods, with equal info AC, B equals 16, V equals 65K, outperforming the bytes baseline at all sizes. While sentence piece performs the best, the gap between equal info AC and sentence piece narrows with scale. Figure 4 compares various models based on their performance metrics of bits per byte, bits/byte, and bytes per step, bytes/step. The primary focus is on the trade-off between computational efficiency, measured in flops per byte, and the quality of text generation, measured in bits per byte. Models like equalinfoac, B equals 16, V equals 256, demonstrate superior performance over traditional byte-level baselines, especially in scenarios where computational efficiency is prioritized. Additionally, models trained on compressed data, such as equalinfoac, B equals 16, V equals 65K, exhibit reduced latency in text generation, making them suitable for applications where system latency is a critical factor. The figure also illustrates a Pareto frontier, which represents the optimal balance between bits/byte and bytes/step, with the 2 billion parameter equalinfoac, B equals 16, V equals 65K, model positioned on this frontier, indicating its efficiency and effectiveness in practical applications. Figure 5 illustrates the performance of equalinfoac with varying window sizes, specifically B values of 16, 32, 64, and 128. When assessing bits/byte to control for compression ratio, an unexpected trend is observed where B equals 16 performs best for most model sizes, while B equals 128 is the second best. This anomaly is attributed to the superior compression rate achieved by longer equalinfo windows. Conversely, when evaluating token/byte, a clear monotonic trend surfaces, indicating that shorter windows are more straightforward to learn. Figure 6 illustrates the impact of using a larger vocabulary size for arithmetic coding-derived methods on both perplexity, measured in bits/byte, and token compression rate, measured in flops/byte. The data clearly shows that increasing the vocabulary size leads to improvements in both metrics for arithmetic coding methods. This suggests that larger vocabularies enable the models to better capture the nuances of the compressed text, resulting in lower perplexity and more efficient token compression. However, this trend does not hold for gzip compressed data, where increasing the vocabulary size does not yield similar benefits. This discrepancy highlights the differences in the coding components of arithmetic coding and gzip, which may explain why larger vocabularies are not as advantageous for gzip. Overall, the figure emphasizes the significant gains that can be achieved with larger vocabularies for arithmetic coding methods, making them more competitive with other tokenization methods. In this section, we explore additional experiments to understand the learnability of different compression methods. First, we examine bitstream tokenization, where both 8-bit and 16-bit chunking strategies are effective, suggesting that tokenization is not the main difficulty. We train two models, a 25M and a 403M, on raw bitstream output from arithmetic compression, finding cross-entropy losses close to the uniform distribution, indicating that the main challenge lies in the AC encoding itself. Next, we look at arithmetic coding, which is difficult for transformers to learn. We set up sequence-to-sequence tasks for compression and decompression, expecting 100% accuracy but finding models perform no better than byte-level language models. Finally, we investigate the impact of vocabulary size, showing that a larger vocabulary significantly improves performance, with most of the gain attributed to structural changes in tokenization rather than the increased text seen during training. Table 5 highlights the challenges transformers face in learning arithmetic coding AC. In a sequence-to-sequence setting, a model proficient in AC should achieve 100% accuracy. However, our models significantly underperform. For decompression, the transformer's improvement over a pure language model of the targets is not statistically significant, p equals 0.07, indicating it cannot effectively use the compressed input. Similarly, AC compression is only learned to 1.7% accuracy. This data underscores the difficulty transformers have in mastering AC, despite theoretical capabilities. Table 6 illustrates the impact of increasing the vocabulary size from 256 to 65,000 tokens in a byte match setting, where models are trained on the same number of raw bytes. The table highlights that the majority of the performance gain persists even in this constrained environment. Notably, All observed performance improvements between different settings are statistically significant, indicating a robust effect of vocabulary size on tokenization efficiency. In this analysis, we compare sentence piece and equal info AC tokenizers. Sentence piece provides a stable and semantic text-to-token mapping, whereas equal info AC is less stable and semantic. We also examined training dynamics, finding that earlier tokens in a window are learned first, with accuracy decreasing for deeper tokens. Lastly, we analyzed bit stream uniformity, showing that non-uniform distributions are more learnable, and that tokenization can significantly impact this learnability. Table 7 compares the tokenization methods of sentence piece and equal info AC. Sentence piece maintains a stable mapping from text to tokens, such as consistently mapping elephants to the same two-token sequence. In contrast, equal info AC shows less stability and semantic alignment, often mapping the same word to different tokens and failing to respect linguistic boundaries like words or morphemes. Table 8 highlights the stability of token-to-text mappings in the equal info AC, B equals 16, V equals 256, tokenization scheme. Specifically, it shows that tokens appearing at the beginning of a window maintain a consistent mapping to text, whereas non-initial tokens exhibit instability due to their contextual significance. This analysis is based on the tokenization of 20 documents, with a focus on instances where specific tokens appear in the first or second position within a window. Figure 7 illustrates the intricate mapping between characters, bits, and tokens within the equal info AC, B equals 16, V equals 256, setting. Each equal info window is composed of 16 bits of arithmetic coding, AC, output, which are subsequently divided into two 8-bit M2 tokens drawn from a vocabulary of 256. The colors in the figure denote whether each character contributes to the first token, the second token, or both within the window. Notably, the initial characters of each window are not well compressed, resulting in the initial 8-bit token often covering only one or two characters. This highlights the challenge of maintaining efficient compression while ensuring the tokens are meaningful and well distributed. Figure 8 illustrates the learning progression of an equal info AC, B equals 64, V equals 256, model within an 8-token window. The model learns earlier tokens first, with tokens number 1, number 2, and number 3 being learned sequentially. The accuracy increases from token number 1 to number 3, likely due to the benefit of additional leftward context. However, the accuracy then decreases from token number 3 to number 5, indicating difficulty in tracking the arithmetic coding, AC, algorithm beyond approximately 32 bits. This trend highlights the model's sequential learning process and its limitations in handling longer sequences within the window. Figure 9 illustrates the shift in empirical distribution as the bit stream is segmented into larger units. The key focus is on the KL divergence of observed n-gram distributions from a uniform distribution across various n-gram sizes. This analysis reveals that while AC compressed data may appear indistinguishable from random data, there are discernible patterns when using other compression schemes like gzip and shorter equal info AC windows. Notably, the tokenized bit stream, as detailed in section 3.4, contains even more information that can be leveraged by M2 for further analysis and understanding. In this study, the authors demonstrate the potential of training large language models, LLMs, over neurally compressed text. This approach offers better compression than standard subword token sequences while preserving learnability, making models more efficient. The method outperforms raw byte-level models in terms of perplexity at fixed inference costs, and it approaches sentence piece performance as model scale increases. Looking ahead, the authors anticipate future work will develop more efficient compression methods tailored for LLM tokenization, potentially achieving higher compression rates and more effective compute allocation. They also suggest exploring interactions between the compressing model and the LLM to improve encoding and decoding accuracy. Thank you for watching.